Hello, everybody. Today I want to present this lecture about make files, make and make files. Um, since we are using make files in the examples for the course, and make files are a very important tool to control the compilation process. It is true that nowadays there are available several tools more sophisticated like auto tools, CMake, but eventually often they just are a let's say a pre-processing that produces make files. And normally they're useful, these more sophisticated tools, when you want to build a professional program that has to be installed in different architectures. And so you want to have something that really controls the architecture where the program is installed, verifies that all the necessary libraries are indeed present, maybe it installs automatically the ones that are missing. But if your objective is just to write a version of program that has to run on your computer, or in any case it is still at a prototype stage, writing directly the makefile is probably even simpler than using those tools. Normally, what happens when you compile a program? The program is made typically by many translation units. Each one has to be compiled. The translation units are made typically by a source file and several header files that are included. And eventually, the executable may also depend on external libraries that themselves maybe have to be compiled and installed. So the compilation process requires controlling the dependencies of all these different components, and eventually update the ones that have to be updated. And Make is indeed a very old now tool that helps to automatize the compilation process. Indeed, what is making? Well, make in its essential form is just a tool to produce files according to a rule. So files that depends on other files. And indeed, the first example that I want to show is not related to programming, just to show you that Makefile indeed is a general tool, is not strictly related to make programs. For instance, in these very simple instructions we see here, I have a set of rules that produce, starting from a file called lecture.tex, that is a tex file, a file called lecture.dvi, that is what is called the device independent format produced from a tex file by the command latex lecture.tex. This lecture.dvi is the prerequisite to produce either a PostScript file to be sent to the printer using the dvi-ps command, or a PDF file to be sent again to the printer or to be viewed on your terminal or on your tablet with the dvi PDF command. So you see, this is the most essential and simplest structure of make commands. You have the target, lecture.ps, the prerequisite, lecture.dvi, and the rule, that is the way to produce a file lecture.ps from a file lecture.dvi. What you see here, the symbol tab, indicates the tabulator character. This is very important because you need the tabulator character to indicate the commands that forms what is called the rules. Okay? So remember, you need the tab, not spaces. Tab. This is instead an example more familiar related to programming. I'm saying that a program called main depends from main.o and funct.o, and to produce main from those two files, I have to launch the compiler, more precisely in this case it will be the linker, and I want to launch it with optimization02, the linker output file main, and the two files that have to be linked together are main.o and func.o. Func.o depends on func.cpp, the source file, and two other files, two header files. And to produce func.o from those files, I have to run gcc -c -o2 because I want optimization, func.cpp. And finally, main.o depends only on main.cpp in this case, and again, to produce it, I have to run this command. So you see, these is the simplest structure for a makefile. And it is summarized here. You have targets that may depend on prerequisites, and these dependence is normally indicated with a single column. There is also a possibility of using two column, but I will not now deal with this with the difference between using one or two. So you have the target column, the list of prerequisites, and then following tab and the command that enable to produce the target from the prerequisite. And you continue like that. You may have more than one command. Here I just recall you again that the tab symbol indicates the tab keystroke. And a thing that I've added here, make sure that your editor is not configured to replace tabs with spaces, because sometimes this is one of the possible configuration, and at least when you are editing a makefile, you must be sure that you don't press tab, but your editor instead put spaces. It has to be a tab, a tabulator character. The one that is identified when you write with the output stream in C++ by \t. So the nomenclature, I've already introduced that. The target is either the file, the name of a file that has to be generated, or the name of an action to be carried out. In this case, we talk about phony targets. A prerequisite is a file or an action required to produce the target. More prerequisites are separated by a space. Don't put a comma, a space. Okay? A command is a statement that makes launches whenever the target is out of date with respect to the prerequisites. So if the target is older of any of the prerequisites, the command will be launched. And the command always starts with a tab. The rule is just the list of commands that produce the targets from the prerequisites. And a directive is a full set of instruction, but is a synonym of rule. So how does it work? Well, the way make works is very simple. When you launch make target 1, the command operates recursively. It looks at the prerequisite, and if no rule for the current target is found, will return. If not, it will check the prerequisite, because the prerequisite may be themselves targets, like here, right? The prerequisite main.o is itself a target. So it will analyze the rule to make the target. It will repeat the process, until all the targets and all the prerequisites are updated. So not finding any rule for a target is an error, okay? In a Makefile, however, you can make things a little bit more interesting by defining variables. Variables are defined in a very simple way. Name of the variable equal, and the list and the list of well, a string in fact that describe what the variable contains. If you have to go to the next line because maybe it's getting too long, you use the backslash and then you may continue to the next line. Sources is again another variable that contains all this list of names. Exec just contains main. And then I can use the variable. To recall the value containing the variable, that is these strings, you have to use this strange syntax. Dollar, parenthesis, the name of the variable. So this translates in main, objects in this list, and here exec is again main, and objects is this list. There are other ways of setting variables. One is this one with question mark equal. This tells if CPP flags has not already been defined, define it as -d and debug. If not, keep the value it has. Okay? So it will define CPP flags as -d and debug only if CPP flags have not been set before. Or you can use plus equal, that works like plus equal in C++. That means you add something to, in this case, LDLibs. There is also another interesting feature. You can specify the variables also at the moment you launch Make. And the specification you give that way, like here, make call CPP flags -03 LDLibs -LDL, these specifications take precedence to the possible definition inside the file. So you can define variable, you can change variables. You can also get variables from the environment, in the sense that if you have defined some environmental variable, those are automatically imported by Make. For instance, if in my shell, in my terminal, I write export cxx equals clang++, and the Makefile does not redefine cxx, the value clang++ will be used for cxx. This is a feature that I've used in the Makefile for the examples to import the value of environmental variables set by the module system if you use the modules. Just for you, if you want to see the environment, that is the exported variable that are currently in your system, just do env. Env is a little command, is a bash command that just lists all the environment variable. Variable can be manipulated in many ways. There are a lot of tools. I'm not going to explain all of them here, but only some that are quite useful. For instance, sources is a variable that contains the name of these two files, main.cpp and other.cpp. You want to have the corresponding object file, that is just replacing cpp with .o. Well, you can do like that. Objects, you use this syntax, that means takes the variable srcs and replace all occurrence of .cpp with .o. Objects or objs will be now main.o, other.o. You can also get all the files with extension HPP in your directory. Then you use the syntax $wildcard *.hpp. The wildcard statement is not strictly necessary. It may work even without, but it is better to use it because it tells Make that the next character, that is the asterisk, is a wildcard. It's not meant to be asterisk, but is a wildcard of the shell. That means any string. Okay. So in this case, probably it works also without, but it's better to indicate when you use wildcard, that is symbols that have a name, a meaning different than the literal meaning, then it's better to use with wildcard. Then we have a lot of predefined and automatic variables, which may be used in what are called implicit rules and in user-defined rules. So we are going to discuss implicit rule and user-defined rules in a while. For instance, let's suppose we have this variable that contains main.o, a.o, b.o, and so on. And I want to say that mains depend on objects, and I have to use what is contained in CXX, that is normally the C++ compiler, minus O, and I have these two strange symbols. These two strange symbols are the prerequisite and the target. This is the target, and this is the prerequisite. So it will be, this symbol will be replaced by main, and this other symbol will be replaced by the objects. I can also do things like that. Take all files that have extension PDF, depends on the same stem with, however, extension .tech. And to generate the PDF from the tech, you have to run PDF LaTeX on the corresponding file. This instead says that all the .o depends on CPP, and to generate the object file from the source file, you have to run these commands. And again, you have here the prerequisites. So we will see that these two last rules are not necessary because Make already knows them, and that simplifies life a lot. But anyway, let's have a more detailed explanation of the previous slide. CSX is a predefined variable that contains the names of the C++ compiler. By default, it's G++, it's a GNU compiler, but you can change it, of course. For instance, you can set it to C-line++. CSX flags and CPP flags are also predefined variables that, however, by default are empty, but you may fill them. And we will see them later on what they mean. This command, sorry, here is uppercase C, while in this previous slide I changed it to CPP, but I forgot to change it here. But anyway, this is a user-defined rule that converts any files named something.uppercase C into something.o. This is an automatic variable that indicates the prerequisite of a target, while this other indicates instead the name of the target. So there are a lot of automatic variables. These are the main ones. File name of the target of a rule, the first prerequisite, the name of all prerequisites newer than the target, the name of all prerequisites with spaces among them, the stem with which an implicit rule matches. I mean, with that you can really create your own automatic rule that applies to all files with a certain extension. But we will see soon that things are indeed simpler. I wanted to present you these slides because it is important to know the basic mechanism behind Make, but we will see that you can get away with those automatic variables. Because Make has implicit inbuilt rules. Make already knows how to create certain targets. For instance, Make has already an implicit rule to update a .o file from a corresponding .cpp or .uppercase-c file. For example, if main.cpp is present in your directory, and in your make file you have just main column main.cpp with nothing else, and you say make main, make will launch automatically this stuff. CXX, that is by default G++, these other variables, these other implicit variables, predefined variables, which are normally empty, -o main, main.cpp, and then this other variable. So that this is done automatically. And so you can personalize the rule by giving values to those variables. So here is another example where I give value to those variables. I'm saying that I want C-lang++ as a C++ compiler. I want opt flags. This is not a Makefile variable, it's my variable. It's a variable that I have created here in the slide, -g. And then I say the CPP flags is -d as float, -e.include, because the include files are in that directory, that the CXX flags is opt flags, that is optimization flags, -w all, because I want all warnings. LD flags is just opt flags, because I have to repeat the optimization also for the linker. That the library that I want to link resides in mylibdir, and they're called libmylib.a or libmylib.so. That the way I want to link is by using the C++ linker. I will tell you why we need that. And then I just write main.o, other.o, other.o, other.cpp, include other.cpp. That's it. Now, if I do make main, the compiler will run the compiler and the linker using C-lang++ as the compiler and using all those options in the compiler and in the linker. So we have a sort of predefined variables that sometimes have got already a default value, sometimes are just empty, and that are used in the implicit rules. So I can I don't have to write the rules myself. I have just to set those variables to the values that I want to use. So the main ones, CSX is a C++ compiler. CPP flags are the options for the preprocessor. Include, define, okay? CSX flags are the option for the C++ compiler. CC flags are the option for the C compiler. FF flags are the option for the Fortran compiler. LD flags are the option for the linker, but not for indicating libraries, other options for the linker. LD libs instead for indicating library. Link.o is a common use at the linking stage. And target.arg is a target architecture when normally you don't change that very often. The macro link.o is the command that Make uses to call the linker. And unfortunately, it has a default. And the default is the C compiler. Since you don't want to use as a linker the C compiler, because you want to have the standard libraries, the C++ standard library, not the C standard library, you should change link.o in this way. Okay, you change it so that now the linker is a C++ compiler, linker flags, well, target arc, because you in the rule written in hardwired in the make file, there is also target arg, even if often it is empty. Well, why it is empty? It is empty because normally you compile for the same on the same machine where you run the program, or on the or at least on a machine of the same architecture where you run the program. But remember, the GNU compiler is a cross compiler. You can compile on your computer, let's say a Mac OS, a Mac PC, a code for a different architecture, even for your cell phone or for your tablet. GNU is a cross compiler. That's why you have this variable. This variable is used only if you compile for another architecture. Normally, leave it alone. It is empty. So there are other useful implicit variables that I use quite a lot in Makefiles. One is rm, that is a variable that contains a command to remove files, and is rm-f normally. Okay, use that because at least you're sure that you're using the right options. Then CC is a C compiler, FC is a Fortran compiler, CPP is a C preprocessor, even you're not going to use it very much. R is a command to produce static libraries, and R flags are the flags for R. That by default is RB. There are which are the common options that you can put in CPP flags? Well, everything that is needed by the preprocessor. So you put in CPP flags the directory of include files, possible preprocessor macro that you want to define, minus the and debug, that is a preprocessor macro. So these is the stuff that normally goes in CPP flags. Okay, what you want to put in CXX flags? Well, the debugging or optimization level. If well, fpeak, we're gonna talk about fpeak when we discuss about the creation of shared libraries. Minus std if you want to specify the standard, the C++ standard you want to use. The warnings, minus wall, minus w extra, or the warnings you want to add, if you want to be pedantic. I mean, all the options that are proper of the C++ compiler. What do you put in LD flags? Well, you put the options for the linker. You recall again the optimization level, so like in CXX flags, but you can say that you want to create a shell library, that you want to link only with static library. This is the default in Linux, that you want to create an executable, but this is the default, so you can avoid it. That you want to set the loader to look in a certain directory for share library. This is something that we will discuss in the lecture about share libraries. The name of the produced file, the output minus O, the name of the executable. Okay? If it is different than the one automatically produced by the rule. So these actually, this last option, you normally don't use it. Actually, it would have been better to take it out and not to make mistake. You don't have to repeat that. Okay? It is necessary only if you want to do strange things using a different name, but normally you don't want. So this is taken out. What is LDLibs? LDLibs instead are the libraries you want to load. So if your code compiles with libraries, you have to specify here, for instance, the directory where the libraries are contained, the name of the libraries, or you can also specify, if you don't want to use this syntax, you can specify directly the full path of the library, okay, the full name of the file where the library is contained. But it has to go in LDLib, so don't put library information in LD flags, okay? I've already told you that you can pass variables as argument and that take precedence, so you can change the CXX flags, for instance. Remember to put the quotes if you have more than one item separated by a space. You can also add, you can also use a plus equal. I'm adding to the CXX flags contained in the make file -03 -WAll. If you want to see all the implicit rules, well, this is a command. And you dump it on a file, rules.txt, and you can see all the implicit rules of make. If you want, just for fun, let's do it here. Oh, come on. Make -p -n -f dev null. Here, now they are on the terminal. You see all the rules. You see, there are many. Okay, so Make already knows how to make your executable from a CPP file. You don't have to write the rules yourself, and this is a great advantage. I've talked about phony targets. A target is called phony if it is not associated to a prerequisite, but it expresses an action. Normally, phony targets are all, that is normally the first target in your program. Clean, this clean, clean for cleaning, this clean for cleaning. Well, a difference normally between clean and this clean, that clean cleans, but not everything. It doesn't clean, for instance, libraries. This clean really cleans everything, okay? Normally, you don't have to do anything, but it is better to specify that those are phony targets. So if you're using clean as a target, as a phony target, it is better to tell make that it is a phony target with this instruction. The reason is that well, it's just for safety, because if it happens that in your directory you have a file that is called all or that it is called clean, then make will get a little bit confused. So while here you're saying that clean is not meant to be the name of a file, it is a phony target. So this is a phony target. Clean, remove. And this clean calls clean, you see, this clean as a prerequisite clean. So a prerequisite can be also a phony target. That is, when you launch make this clean, it will launch clean that removes all the object file, and then it will remove also main. And this is just a more complex example, but not very much complex. I've set CXX flags, the source, the objects are automatically deduced from the source, the headers are all the files with app in this directory, the exec is called main, the for is called all as a prerequisite exec, clean removes, exec depends on objects, and objects depend on sources and on headers. That's it. All the rest is automatic. Sometimes the prerequisite may be in other places, not in the current directory, not in the directory where you are launching Make. Well, you can say to Make that the search has to be extended also to other directory. For instance, in .includes and in my home includes. You can also use vpath lowercase, that is even more powerful. You may say that all the files that has extension .hpp has to be looked in the current directory and in the directory, in the subdirectory include of the current directory. This is a subdirectory include of the current directory. And you can put a list. You don't need just one. You can do like here. You can include other makefiles. That is something that I use a lot in the makefiles for the examples. You can include other makefiles in the makefiles with include. There are two forms. This form, include file name, will stop make with an error if the file is not present or is empty. Okay? If you want instead make to ignore the error, that is, if the file is not present, okay, doesn't matter, you have to put a minus before. Minus include file name. And here is the last slide, let's say, of the basic stuff. Now it's not very basic. Now, one of the problems with the C++ translation unit is that it may depend on header files, and header files may depend on other header files, and so on and so on. And it's very complicated to keep track of all the dependencies. And so far, we have to specify the dependencies. No, also in this case, okay, the dependency, the header files, I said are all the header files in this directory, but maybe there are other header files, other .cpp maybe depends on other header files, or the header files in this directory may include other header files. So how can I keep track of all the possible dependency? There is an automatic way, and to that purpose you can use directly the compiler. The compiler, at least the GNU compiler and CLang compiler, have a set of options. They all begins with uppercase M, that exploit the preprocessor to generate automatically a file containing prerequisite. Actually, it doesn't generate a file. It will just dump it on the output stream. It is up to you to put it on a file. Okay? For example, let's see, this is what I'm using in the makefile of the example. I have a file called make.dep that depends on all the sources. So of course, I need to know which are the sources that generate my code. And this file is included with minus include, but it is automatically generated. And which are the rules to generate this file? Well, the rules are here, and here I forgot to put the tab. But now you remember, no, that you have to put a tab. Remove make.dep, remove the old ones, and then for all files, this is a bash script. Okay, this is a bash script. For all file in sources, go to the next line because the word was too long, run cxx with the CPP flags because I need to know, for instance, where to look for include files, with the options -mm, taking F, I have to put the $$ because F is a bash variable, not a make variable, and to address bash variables, the content of bash variables in a make, I need to use $2. So this is f, this is a for loop, and put everything in make.dep, but I'm using two arrows here to, I don't know how to call it, triangular brackets, to say that it has to be appended. So every time is appending a new rule so that it finds on this file, make.dep, and then include make.dep. So this is an example of a file produced by that technique. This is automatically generated. Read parameters.o depends on read parameters.cpp, get bot.hpp, read parameters.hpp, parameters.hpp. Parameters.o depends on all of these dependencies has been found automatically by this instruction. -mm tells to look header files, but excluding system header files. If you use other options, for instance, if you just put -m, you are going to find among the dependencies also the files of the standard library, for instance, vector and so on and so. I don't want that. I just want the dependencies on the files that are reasonably under my control, okay? There is also an external utility called makeDepend that does more or less the same thing, but I prefer to use a compiler because certainly the compiler knows where to look for include files, right? I mean, it is its job to do it. This is an overview of some useful option of make. If you call make with -j and a number, it compiles in parallel using n processes. So if you have a computer with more than one thread, you can compile in parallel. This is useful if you have to compile, of course, big programs, otherwise it doesn't make any sense. -d gives more details of compilation. -b unconditionally make all targets. Make normally compiles only the targets that are out of date with respect to prerequisite. With -b, uppercase B, it will ignore and it will make all targets in any case. These are we already know. You can specify a file different from makefile with the option -f, so the file doesn't need to be called makefile. Makefile can have uppercase m or lowercase m, is the same. So the standard file for makefile is called makefile, but you can specify that you want another makefile. -n, also minus just print, prints the commands that will normally be executed without executing them. This can be useful if you just want to know what make is gonna make without actually doing it. And these we have already seen. Print the database and does not execute any makefile. Now we have a set of slides with more advanced stuff. I don't want to go in detail on them. I will leave the slides. This is more advanced stuff, and I don't want really to make this video too long. So the first, you can launch make from make. So you can have make that launches make. This is useful sometimes if you want to launch two different versions. Okay? So the optimized one and the not optimized one. I'm using that also in the makefile of the example. You can, when you launch another makefile, you may want sometimes to export some variables to the sub makefile, and then you have to declare the variable explicitly, export variable, or you can say just export and all variables will be exported. This we have already seen, pattern substitution, so it's just a repetition actually. You can have conditionals. If CC and GCC, do this, otherwise do that, okay? You can call shell commands. We have already seen it in one case, but in general, you can call all shell commands, so you can inside your bash file. The only thing that you have to remember is this $$ rule. This is another example of remember that the Unix shell, and bash in particular, has more than dozens of very powerful commands that make life easier. So it is very useful to have the possibility of calling bash from make. What else? A lot. Multiple target per rule. Functions for working with files and adding different directories. There is all in the make manual. It's very well documented, and there is also a book that is actually a pretty printed version of the manual. So for the real gurus, you may want to go further and want to use the auto tools or CMake. CMake is also integrated in CLion, so it may be easier to use CMake. Remember that they are more powerful, but they're not much simpler than just writing a makefile, if the objective is just to write a program that has to run on your computer. If you have to write a program more professionally that has to be deployed on different architecture, different computer, distributed on the web, then it's better to use either CMake or the auto tools or other tools that are available that I'm not mentioning here. Okay, that's all. Enjoy making and ready for the next video.